One of the methods for computing Galois groups is reduction mod p. The technical issue that arises here is that fields like rational numbers cannot be reduced mod p because of the possible problems with zeros in denominators. So we need to work with rings associated with field extensions. In order to define such rings, we introduce the notion of integrality, and we give the following definition. Let S be an extension of a ring R. So let this is a ring extension. An element S in the ring S is called integral over R if there exists a monic polynomial f with coefficients in R such that f evaluated at S is equal to 0. So elements in S are called integral over R if these are roots of monic polynomials. As an example, let's consider the ring extension of integers, and let's go from integers to real numbers. Here we see that cube root of 2 is integral over z. So because we have a monic polynomial x cubed minus 2 for which this is a root. If we take 1/2 on the other hand, so this is not integral over z. So the minimal polynomial here is 2x minus 1, which is not monic. And we're going to see today that in fact there is no monic polynomial with integer coefficients for which 1/2 is a root. Clearly, all elements that are integral over z are algebraic numbers. And we give the following definition. Elements of Q bar, the algebraic closure of Q, which are integral over z, are called algebraic integers. So, for example, cube root of 2 is an algebraic integer, but 1/2 is not. We have the following lemma. Let S be an extension of a ring R and let S be an element in S which is algebraic over R. Then there exists an element R in the ring R which is non-zero such that R times S is integral over R. This lemma is the analog of clearing denominators in rational numbers. So if we have a fraction, then we can multiply it by its denominator, and the result will be an integer. For proof, so we say that since S is algebraic, then this means that there exists a polynomial an x to the power n plus a1x plus a0, so let's call it f of x, such that f of s is equal to 0. And we may assume that the leading coefficient is non-zero. So here we claim that as r, we can take the leading coefficient an. The fact that f of s is equal to 0 means that an s to the power n plus an minus 1 s to the n minus 1 plus a1s plus a0 is equal to 0. So now multiply this by an to the n minus 1. So then we get an to the power n Sn plus an minus 1 an to the n minus 1 s to the n minus 1 plus a1 times an to the n minus 1 s plus a0 times an to the n minus 1 is equal to 0. And this can be written as an times s to the power n plus an minus 1 an times s to the n minus 1 plus a1 times an to the n minus 2 times ans plus a0 times an to the n minus 1 is equal to 0. And this tells us that rs, which is an times s, is a root of a monic polynomial x to the n plus an minus 1 x to the n minus 1 plus a1 times an to the n minus 2 times x plus a0 times an to the n minus 1, which is the claim of our lemma. Our next lemma is about unique factorization domains. Let R be a unique factorization domain, or UFD for short, with a field of fractions k. Then elements of k that are integral over R are precisely elements of R. In particular, this says that 1/2 is not integral over Z. Here we have that Z is a unique factorization domain and Q is its field of fractions. And so this lemma says that the only rational numbers that are integral over Z are integers themselves. Let's give a proof. So suppose the element S in K is written as A over B, and A and B are elements of R. We may assume that the numerator and denominator, A and B, have no common prime factors. Otherwise, such factors can be cancelled out. Suppose S is integral over R. This means that there exists a monic polynomial for which A over B is a root. So we have A over B to the power n plus Cn minus 1 A over B to the n minus 1 plus C1 A over B times plus C0 is equal to 0, where Cj's are in R. Then if we multiply by B to the power n and move the tail to the right hand side, then we get A to the power n is equal to minus B times Cn minus 1 A to the n minus 1 plus dot 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 C1 B to the n minus 2 times A plus C0 B to the n minus 1. And since R is a unique factorization domain, so we conclude that a to the power n is divisible by every prime factor of b. Because here we have a factor of b in the right-hand side. But again, because we have a unique factorization of a into primes, so this tells us that a is divisible by prime factors of b. And this tells us that b is a unit, which implies that a over b belongs to R. Next, let us give a couple of definitions. Let S be a ring extension of R. We say that R is integrally closed in S if elements of S integral over R are precisely elements of R. Of course, we mentioned that every element A in R is certainly integral over R, because it's a root of a polynomial x minus a. And this polynomial has coefficients in R. And the next definition is that domain R is called integrally closed if it is integrally closed in its field of fractions. So the previous lemma told us that if R is a unique factorization domain, then this means that R is integrally closed. Let us give an example of a domain which is not integrally closed. So let's take R to be Z with a joint square root of 5. Here, the field of fractions is Q with a joint square root of 5. Let's take the element of golden ratio. So this is phi, which is 1 plus square root of 5 over 2. So this is in Q with square root of 5. One can check that the minimal polynomial of the golden ratio is x squared minus x minus 1, which is monic. So this tells us that phi is integral over R, but phi is not an element of R. So this means that Z with square root of 5 is not integrally closed. As a corollary, we see that this ring is not a unique factorization domain. And indeed, in this ring we have 2 times 2, which is 4, is equal to square root of 5 plus 1 times square root of 5 minus 1. And then we see that all these factors are irreducible, and this factorization is not equivalent. square root of 5 plus 1 is clearly not a multiple of 2. Note that if we take the ring Z of phi, then these two factorizations become equivalent. So because square root of 5 plus 1 is equal to 2 times square root of 5 plus 1 over 2. And this element phi is a unit. So that is invertible. The main result that we're going to prove in this lecture is the following. So we have a theorem. Let S be a ring extension of R. And let T be the set of elements in S such that S is integral over R. Then T is a ring, so that is, it is closed under addition and multiplication, and T is integrally closed in S. That is, elements of S that are integral over T are just elements of T. The proof of this theorem is based on two lemmas. So the first lemma says that let S be a finitely generated ring extension of R. So that is S is equal to R with the joined elements S1 through Sn. Assume that each Sj, where j goes from 1 to n, is integral over R. Then S is finitely generated as R module. As a proof, we observe that, so if we take S to be integral over R with monic polynomial x to the power m plus am minus 1 x to the m minus 1 plus a1x plus a0, then we get a reduction rule that s to the power n is equal to minus a m minus 1 s to the m minus 1 minus a1s minus a0. And it follows that for every k, s to the power k belongs to R module generated by the set s to the m minus 1 through s and 1. If k is less than m, then this is trivial, and if k is greater than m, this claim follows from this reduction rule. Let m1 through mn be degrees of monic polynomials corresponding to the generators S1 through Sn. Then we see that S is generated as R module by the finite set of products S1 to the power K1 dot 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 Sn to the power Kn, where for every j from 1 to n, Kj is strictly less than Mj. Since S is generated by elements S1 through Sn as a ring, then as an R module, it is generated by all the monomials in variables S1 through Sn. But then, because of the reduction rules, we can lower degrees of these monomials and get uniform bounds for them. So we get that as an R module, the ring S is finitely generated. Let's consider a couple of examples. If we consider the extension of Z to Z with cube root of 2, then we know that cube root of 2 is integral over Z. And as Z module, Z with extended cube root of 2, this ring is generated by the set 1 cube root of 2 and the square of cube root of 2. Every element of this ring is an integral linear combination of these three elements. As our second example, let's consider an extension of Z with 1/2. This ring consists of rational numbers whose denominators are powers of 2. And we can see that this is not finitely generated as a Z module. Because any finitely generated Z submodule in this ring will have uniform bound on degrees of powers of 2 in denominator. And we also see here that 1/2 is not integral over Z. Our second lemma is complementary to the first one. Lemma. Let S be a ring extension of R such that S is finitely generated as R module. Then every element of S is integral over R. Let's give a proof. Let x1 through xn be generators of S as R module. And consider an arbitrary element little s in S. We need to show that this element is integral over R. So let us multiply S by each generator, S times xi. The result is going to be an S, and because S as an R module is generated by x1 through xn, this can be written as the sum over j from 1 to n, aij times xj, where aij are elements of R. Consider the matrix A that's made of these entries aij's. So this is a matrix with values in the ring in R. Then this system of equalities may be written in a vector form as A minus S times identity acting on the column vector x1 through xn is equal to the 0 vector. Let B be the formal adjoint of A minus Si transpose. This is a matrix that's made of cofactors of the matrix A minus Si. Then we know from linear algebra that B times A minus Si is equal to determinant of A minus Si times identity matrix. If we multiply this vector equality by matrix B, so we get that determinant of A minus Si times identity matrix applied to x1, xn is a zero vector. In particular, the operator that is on the left is a zero operator. And applying this operator to element 1 in the ring S, we get that determinant of A minus Si is equal to 0, which means that S is a root of characteristic polynomial of matrix A. And this polynomial is monic and has coefficients in the ring R, since the entries of matrix A are in R as well, which tells us that S is integral. And this is what we had to prove. Now, with these two lemmas, we can prove our main theorem. So let's recall. So here we have a ring extension S of the ring R, and we can see that T, the set of elements in S, which are integral over R. And we make two claims. So we need to prove one, that T is a ring, so that is it is closed under addition and multiplication, and two, that T is integrally closed in S. For part 1, let A and B, two elements of T. We need to show that subring R generated by elements A and B is in T. The elements A and B are integral over R by definition of the set T. And by lemma 1, this subring R of AB is finitely generated as R module. And by lemma 2, every element of this subring is integral over R, which means that this whole subring is inside T. So this proves that T is closed under addition and multiplication. Now let us prove the second claim. Suppose S is integral over T. This means that S to the power n plus an minus 1 s to the n minus 1 plus and so on a0 is equal to 0, with aj's being elements of T. Consider a subring generated over R by the coefficients of this polynomial. So an minus 1 up to a1 and a0. Let's call this ring P. By lemma 1, P is finitely generated as R module. And let's denote the generating set by B1, Bm. So these are generators. Then the ring generated over R by elements S, an minus 1, a1, and a0 is generated as R module by the set b1 s to the power j dot 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 bm s to the power of j, where j is between 0 and n minus 1. So this set is finite, and by lemma 2, every element of this ring is integral over R. So in particular, S is integral over R. And we prove that any element which is integral over T is in fact integral over R, that is, already belongs to T. So T is integrally closed in S.